I am going to mention nuclear fission and of course its cousin in a minute, nuclear fusion, because this is where an awful lot of what people think about associated with nuclear chemistry comes from. Nuclear fission is where a big nucleus, and anything bigger than iron 56 can do it, splits into smaller ones and then usually gives out some neutrons. Of course, the classic is uranium-235. If uranium-235 hits upon a neutron, it turns into the metastable uranium-236, which then very quickly smashes apart into 138 xenon, 95 strontium, and 3 neutrons. Okay, so you can see big nucleus splitting up into smaller ones, and you've converted 1 neutron into 3 neutrons. Now, you get lots of different products, and I've just pulled out a few example ones, but other ones that you might have seen mentioned in, for example, Chernobyl, 131 iodine, a cesium isotope, and so on, and so on, and so on. The important thing here is on average, right, because you lose some neutrons, you get an average of 2.5 neutrons made for every one of these actions, but you only need 1 neutron with another nucleus of 235 to keep it going. So you get a different type of chain reaction. In the core material, I talked about chain decays, where one unstable nucleus decays to another unstable one, which decays to another unstable one, which decays to another unstable one, and so forth. That's a nice one type of chain. This chain is where when uranium-235 starts into fission with 1 neutron hitting 1 nucleus, it produces about 2.5 neutrons on average to be used for another 2.5 uranium nuclei. And so you can see that it kind of goes viral, if I could use a more modern technology, right? Every single one that happens allows another 2.5 to happen. So you get these amazing chain reactions going on. Now, if you only have a few atoms of uranium-235, it's no big deal. But there is something called a critical mass that I know you have heard of. And that is where you have physically enough uranium-235 to say that you've got enough there that at least 1 neutron that is produced here will go on and find another uranium-235 isotope. Nuclear fission, of course, associated with the bomb, also associated with the production of nuclear energy, and we'll talk about that in a little bit. Now, of course, the opposite, if you like, of nuclear fission is nuclear fusion. That's where smaller nuclei combine into bigger ones. And in theory, anything smaller than iron 56 can undergo fusion. Of course, what one actually sees is with much, much, much smaller nuclei. A couple of examples, the 2 isotopes of hydrogen fusing together. So deuterium, the stable, hydrogen-2, tritium, the radioactive, hydrogen-3, come together to make a helium nucleus and a neutron. This is one of the classic ones, of course, associated with fusion. This is what goes on mostly in the sun. It was also what people thought was happening with cold fusion, because some scientists messing around with deuterium and tritium noticed a bunch of helium being formed. And instead of finding out where the helium was coming from, they assumed, wow, we have fusion taking place at room temperature. 1989, 1990, a nice little story for you to read in between your studies. Now, the classic one, lithium-6 with a neutron, goes to metastable lithium-7, so-called compound nucleus, which then breaks apart to give you the helium nucleus, nice happy helium nucleus, and some tritium. So nuclear fission, very, very important. Big nucleus splitting up into smaller ones with chain reactions allowed because the product is one of the possible reactants. Nuclear fusion, smaller nuclei combine into bigger ones.